we saw what is known as the so-called monotone class. Yes, so where did we stop? We stopped at what is known as the so-called monotone class theorem. Yeah, this was the one. So let Sankit, let A be an algebra of subsets of omega. Then the monotone class generated by this algebra coincides with the sigma. Yeah. So we were looking at the proof. So in fact, so let me not get into the details, whatever we have already done. So we are supposed to show that, in fact, enough to show that this M of A is an algebra. Right. Right. So first thing, so we'll have to show that it is closed under complements and finite union. Right. So first thing, what did we do? We formed what is known as MC. All those E in M of A says that E complement belongs to M of A. Yes. So we showed that this MC is a non-empty monotone class containing A and contained in MA. Therefore, MC equal to MA. That is, MA is closed under complements. This was the first one that we saw, right? And then for union, for each E in A, we let ME as all those F in M of A says that E union F belongs to M of A. So we showed that this ME is a non-empty monotone class containing A and contained in MA. Therefore, ME is equal to MA. Right. Fine. So up to this we saw. And then now, so what you do is now for E in MA, As usual, let same thing. ME equal to all those F in MA such that E union F belongs to MA. Right. We are not going to prove anything about this. Right. Now what you do is that let script M equal to all those E in MA that ME is equal to ME. So what does it tell us? Therefore, E belongs to M. Well, so first thing, so is a script M non-empty? Is script M non-empty? Is script M non-empty? Is script M non-empty?
Yes, sir.
Why?
Sir, we have just shown that for an E belonging to A, ME equals to MA, and so we can take any element of A
Yes,
for that.
exactly. Exactly. In fact, the whole of A is contained in script M. So note that if E belongs to A, then ME is equal to MA. That's what we have shown. Well, if E belongs to A, so then I'll simply write this one. Then ME equal to MA, and hence E belongs to script M, implies A is contained in script M, which implies that the script M is non-empty. Yes, so it's a non-empty collection. First thing. Second thing, E belongs to script M. If and only if, yes. So what does it tell us? E belongs to script M if and only if. When will that belong to? What is ME? Well, if and only if the corresponding ME is equal to M of A. Well, but what is ME? Just now we have defined, just see last line, the first line.
Collection of all those subsets which whose union with E is contained in MA.
But ME should be same as M of A. That means
MA is closed under uni.
if and only if E union F belongs to MA for all F in MA. So therefore, this implies that the scriptum is a, what does it tell us? The scriptum is a
Algebra.
Scriptum is a
Algebra.
Where have you shown that it is closed under? Well, I'll simply say this one. Is closed under taking finite union. Well, you can also show that the scriptum is closed under complements. I'll simply leave it as an exercise. And therefore, these two together will imply, therefore, the scriptum is an algebra and therefore it's a well, rather than showing all these, well, sorry, you don't have to show even, well, something more can be actually shown. Not only that it is closed under finite union, well, I'll simply say this one. Scriptum is closed under countable operations. That is, well, under monotone operations. I'll simply say this one. The scriptum is closed under monotone operations. Yeah, this is not, we have already done all the things, whatever we wanted. Yeah, therefore this should not be difficult. So therefore, the scriptum is a monotone class. That's it. So this is a monotone class containing A and contained in A. So that implies that the scriptum equal to M of A. That is, M of A is closed under finite union. That's it. So we have already shown, right, that script M is M of A is closed under complements. Now we have shown that is closed under finite union. That's it, done. Yes. So these are the two things. Right. So therefore, script m of a is equal to sigma of e. That's it. This is what we wanted. Right. Fine. Now let's move on to a new concept, what is known as abstract measures. Right. So initially we started with m star as a concept which generalizes the notion of length. That's what we wanted. That is exactly where we started with. Right. Fine. And therefore, in order to generalize the notion of length, we defined this m star. Well, this m star is non-zero in the sense that there are sets whose m star is non-zero. Fine. It is monotone. The main thing that we had is what is known as countable finite subadditivity and countable subadditivity, because there are sets for which additivity fails. There are disjoint sets for which additivity fails. But then, when you restrict it to the class of Lebesgue measurable sets or family of Lebesgue measurable sets or the collection of Lebesgue measurable sets, there it had more properties. In fact, it satisfies what we expected, what is known as the countable additivity on pairwise disjoint sets. Right. So which means what? In fact, so the script m, which is a collection of Lebesgue measurable sets, or well, rather than I'll simply say sigma algebra of Lebesgue measurable sets. This is script m, and then when you restrict m star to m, so this is countably additive. Well, and this one is known, m star of mt is 0. Right. So these are the two properties that we are going to make use of. So now let's get into the definition. Yeah, so before I get into the definition, let me say one more thing. So this pair is what is known as a measurable space. Right, so this pair is called as a measurable space, wherein this omega is any set, given set, and this is the sigma algebra. Right. Right. Now let's get into the definition. Let omega comma a be a measurable space. A function mu from a to 0 comma infinity, close to 0 comma infinity, is called a measure on omega comma a if first one, mu of the empty set, it should be 0. Second thing, mu of union over n in n, en should be same as summation over n in n, mu of En for any countable disjoint family. In fact, pairwise disjoint, countable pairwise disjoint. N in N from the sigma algebra A. Yes, so any function mu defined on a sigma algebra to 0, infinity is called a measure if it is 0 on the empty set and if it is countably additive. Any function which is 0 on the empty set and is countably additive is what is known as a measure. Yes. Now, do you have an example?
You can take the trivial example now, like if I define A to be phi and the whole of the set, when phi goes to 0 and whole of the set goes to 1.
1.
Anything like that
1.
should.
Except the empty set.
Sir, the set of Lebesgue measurable space, I mean Lebesgue measurable set, and the
That's a sigma
function is
algebra.
Lebesgue outer measure.
Exactly. Yeah, Mahesh, I'll come back to your example.
Okay, sir.
First one, choose omega to be R, A to be script M. Right. Then M star restricted to this M is a measure. This we have already verified. All the details needed to prove this is already done. We have already finished all these. Now, so what are we going to do? So now we are going to set the definition. Yes, so we'll write by script M, only M. What is this? This is M star restricted to script M. And this measure is what is known as the Lebesgue measure. Right. Fine. Yeah, so in many books you will find Lebesgue measure, the notion of Lebesgue measure or Lebesgue integration. There are many books. Now that there are lots of books on Lebesgue measure and Lebesgue integration. So what they wanted to say is nothing but this M. Right. So you choose omega to be any set. And A to be 2 raised to the power omega. Yes, so I am coming to the example that was given by Mahesh. So define mu from 2 raised to the power omega to 0, infinity as mu of E equal to 0 if E is just an empty set, 1 if E is non-empty. This is what you wanted, right, Mahesh?
No, sir, no, sir. Actually, I
Then,
was taking A to be just phi and hold the set. Like, not just
okay, fine. Good. Sorry. Okay. Fine. Good. Yeah, so this is, you can notice that this is a measure. Right. So this is an example for a measure. Right. Correct. Yeah, so there are, let me, so this is what is known as a trivial measure. So omega be any set. And then you choose A to be 2 raised to the power omega. Right. And then you define mu from A to 0 comma infinity as mu of E equal to number of elements in E. Yeah. So again, you can verify that this is a measure. Mu is a measure. I'll simply leave it as an exercise. Not a difficult one. So this measure is what is known as counting measure. Fourth one, omega is any set, and well, you choose to be, well, in both these examples you could have chosen A to be any sigma algebra, doesn't matter. Mu from A to 0 comma infinity given by, well, what you do is fix any x naught in omega. So this, let me call it as mu x naught, because it is going to depend on this x naught. Mu x naught of E as 1 if x naught belongs to E, 0 if x naught doesn't belong to E. Again, so the second example, whatever is given here, it's a special case of this. So again, you can verify that this mu is a measure. It's again leave it as an exercise. Yeah, so this is what is known as the Dirac measure, centered at x naught. Yeah, the previous one is the counting measure. This is the Dirac measure centered at x naught. Right. Right. Well, so this pair, this triplet, omega A mu. That is, you have a set, a sigma algebra, and a measure. This is what is known as a measure space. This is what is known as a measure space. Yes, so you say that this mu is a finite measure if mu of omega is finite. Yeah, then in this case, this triplet is what is known as a finite measure space. You say that this mu is a probability measure if mu of omega is 1. So in this case, this triplet is what is known as a probability space. Third one, mu is said to be a sigma finite measure if there exists En n in n. You get a countable thing such that mu of En is finite for all n in n, and the omega can be written as the union of. Yes. So in this case, this triplet is what is known as a sigma finite measure space. Right. So, so these are the terminologies that we are going to use in measure theory. Well, these are very standard in measure theory, and these are the corresponding terminologies in probability. One is set, omega. Here they call it as sample space. Same thing. Second one, here we have what is known as a sigma algebra. In the context of probability, they call it a sigma field. Here we have so mu is from a to 0 comma infinity, while there it is only very specific. Mu is from a to 0 1. And then, well, here we are the next one that we are going to do is what is known as, well, here we call this as what is known as a measure. There it is called as a probability. Well, next one after this measures, we are going to see what is known as measurable functions. Maybe mostly after minor one, we'll be looking at what is known as the so-called measurable functions. Here they call it as what is known as the random variables. In the context of measurable functions, we are going to define what is known as almost everywhere. There they call it as almost surely. And then we are going to do what is known as the most important thing, what is known as integration. Here it is what is known as expectation. So the major difference in probability theory lies what is known as the so-called convergence theorems. That is what are known as not the what we do as a monotone convergence or dominator convergence or Parto's lemma. Of course, even there it makes sense, but main thing is what is known as limit theorems, what is called laws of large numbers, that is weak law of large numbers, strong law of large numbers, and central limit theorem. These are the main pillars of probability. And then, of course, so once you have this, then you can speak about many things there. Various kinds of convergence. Of course, even those things make sense, but the main thing is what is known as the convergence in distribution, its characterization in terms of characteristic functions, and then the central limit theorem properties. These are the things that are very, very important in the context of probability. Otherwise, well, so that is the reason it is very, very important, and they have got lots of applications in so many areas. Therefore, it is very, very important. Otherwise, there is nothing very special. The speciality lies in those theorems. Central limit theorem, laws of large numbers, the proof, and all those things. Right. Fine. Yeah, now let's look at some examples. First one, as usual, you look at R with these sigma algebra of Lebesgue measurable function sets and the Lebesgue measure. So this is an example for what is known as a sigma finite measure space. Why is it a sigma finite measure space? Why is it a sigma finite measure space?
Because I have intervals which are of finite measure but whose union make up whole of the R.
Exactly, very good. So you choose En to be minus n to n. Yeah, so measure of, in fact, so m of En is finite. And R can be written as union over n in n, En. Yes. Right, therefore it's a sigma finite measure space. Second one, you choose omega to be 0, 1, and then what you do is A as the Borel sigma algebra. Doesn't matter. You could have chosen even Lebesgue measurable sets restricted to this omega, but Borel sigma algebra on omega. Right. So what is the measure? It is, look at the Lebesgue measure restricted to A. Just restricted to A. So notice that the Lebesgue measure, Borel sigma algebra is contained in the sigma algebra of Lebesgue measurable sets. Maybe. Yeah, so good exercise here is that show that script M is contained in BR. Sorry, the other way. Other way. Yeah, this should not be difficult. Well, in fact, why is it true? Because, well, Borel sigma algebra is generated by
Open interval.
intervals, finite intervals. In fact, open intervals, and all open intervals are Lebesgue measurable. That's it. That shows. Right. So just restrict it to A. Then this triplet omega script A M. Well, I should write it as a mu. So what can you say about this mu? What is mu of omega in this case?
Probability space.
Yes, so this is a probability space. So in fact, mu of omega is 1 because mu of omega is just m of 0, 1. And that's exactly 1. Right. So here are some familiar properties that we already know for Lebesgue measure. I'm just repeating for the general measure, but the proofs are one and the same. Omega A mu be a measure space if E1, E2 belongs to A with E1 contained in E2, then mu of E1 is less than or equal to mu of E2. Yes. How does it follow? How does it follow?
We get E3 such that E1 union E3 is equal to E2.
Right? What is E3?
Since A is a sigma algebra, we can get E3 as like E2 intersection E1 complement.
That's it, done. That should tell you. Second one is that if E1, E2 belongs to A with E1 contained in E2 and measure of E2 is finite, then mu of E2 minus E1 is equal to measure of E2 minus measure of E1. Yeah, this first difference is the set difference, while the second one is the difference between numbers. E2 minus E1 is the subtracting E1 from the set E2, while the second one is subtracting the number mu E1 from the number mu E2. So the second, what is there on the right hand side is the subtraction between scalars, while what is there on the left hand side is the subtraction between sets. Yes, so the proof is quite easy. So please do it. Yes. So I have only 5 minutes left, but anyhow, yeah, let me try to do one what is known as the continuity property of measures. Right. Okay, so what do you mean by a continuous function? There are various characterizations. Can you give, well, what is a continuous function? First thing, let's begin with that.
Inverse image of open sets is open sets.
Fine, very good. But that I can't use it here, right? There is no open set in the measure space, so I can't use it. And then anything else?
Sequential criteria.
What is that sequential criteria, please?
If a sequence goes to x, then function fxn goes to fx. Like
For every sequence xn converging to x, fxn should converge to fx. So such a function is what is known as a continuous function. Yes. So we are going to make use of it, right? So the simplest one among them are what are known as the increasing, decreasing. So we'll first start with an increasing sequence of sets. So let omega A mu B measure space. Measure space, and AN belongs to A be such that they are increasing. AN is contained in AN plus 1 for all n in n. Yes. Then mu of AN converges to mu of the limit. What is the limit? It's exactly, well, I'll write this way. Union over n in n. Proof. Yeah, so I'll simply say this one, which we have already done this. So write union over n in n, AN as union over n in n, BN, where BKs are pairwise disjoint. Union K running from 1 to n, AK, the same as union K running from 1 to n, BK for all n in n, and union over n in n, AK is equal to union over n in n, sorry, AN, there should be BN. This you know how to do it, so I'm not going to do it. Yes. Therefore, measure of a union over n in n, AN, this is what we wanted, which is same as union over n in n, BN, right? But BNs are disjoint. So this is same as summation over n in n, mu of BN, well, which I can write it as summation n running from, well, I will write it as with a different, K running from 1 to infinity mu of BK. This infinity, I can write it as limit n tending to infinity, summation K running from 1 to n mu of BK. Now, what are these things? I think we are nearly done. Limit n tending to infinity. This is going to be mu of union K running from 1 to n BK. Well, just what we saw. So same as limit n tending to infinity, mu of union K running from 1 to n AK. But all these AKs are increasing. Therefore, this is same as mu of AN. That's it. And that's exactly what we wanted. Right? Yeah. So there are few more. What happens for decreasing? What happens for the general? So these are the things I have. Yeah. In the next class, we should be able to finish it. Yes. So with this, let me stop today's lecture. If you have got any doubts, you are most welcome.